Okay, so if you're listening to this, maybe you're sitting down, maybe lying down on something soft. Chances are, like 99% certain, you're on flexible polyurethane foam, PU foam. It's everywhere. It's lightweight. It's durable. It totally changed how we think about comfort, especially sleep. But how is it actually made? It seems simple, but it's not. We dove into the sources you sent over because, well, we figured you're curious about the science behind everyday stuff. So our mission today is pretty clear. Let's trace how PU foam gets made, right from the basic chemicals, which, yeah, often started from crude oil, all the way to that complex mattress with all its layers that shows up in your door.
It's definitely more than just mixing stuff together. It's really about precision chemistry, chemical engineering even. Getting that light, bouncy structure takes very specific ingredients and, crucially, very tight control over the whole process. We'll pull out the key bits for you how they make it, like the slab stock method, safety aspects, and what's happening with sustainability, which is actually a pretty big focus now.
All right, let's start at the beginning then. The basic ingredients. You've got polyols, what do the sources say? Long alkoxy chains. Sounds complex. And diisocyanates. Those are the two main players.
Exactly. Those are the fundamentals. And the specific diisocyanate you choose really changes the foam's final properties. For your typical mattress foam, the flexible, resilient stuff that mainly uses TDI, toluene disocyanate.
TDI, okay.
But if you want that slow-moving, contouring, memory foam or viscoelastic foam.
Yeah, the fancy stuff.
Right. For that, you generally switch to MDI, which is methylene diphenyl diisocyanate. MDI is structurally a bit more complex. It can create more connections, more cross-linking between the polymer chains as the foam forms.
Cross-link, like making a denser web.
Sort of, yes. It creates a structure that resists quick changes. That extra cross-linking is what gives memory foam that really high viscosity, that slow recovery that lets it mold perfectly to you.
Okay, so it's not just marketing. TDI and MDI foams are chemically different beasts.
Yeah.
Got it. Now, how do they actually react? You mix them and poof?
Not quite poof, but close. You mix the polyols and the isocyanates, but you also add water, some catalysts to speed things up, and other additives. The water is really key here. It reacts to produce carbon dioxide gas, CO2.
Okay.
And it's that gas bubbling through the mixture that causes it to expand, rise up and create millions of tiny interconnected bubbles or cells. That's what turns the liquid into a light, springy, solid foam.
So it is kind of like a chemical version of bread rising, creating that airy structure. The sources made a comparison to baking a cake. Get the recipe slightly wrong.
Oh, absolutely. The precision is critical. Like, change the amount of water just a tiny bit or mess with the catalysts that control the reaction speed.
Yeah.
And you completely alter the foam's density, how firm it feels, everything.
And the sources mentioned potential disasters too, right? If the mix overheats or isn't blended perfectly.
Yes. The reaction generates heat. It's exothermic. If that's not controlled or if mixing isn't uniform, you can get these huge internal voids. They call them blowholes.
Blowholes.
Yeah.
Sounds bad.
It is. Big, weak spots that basically ruin the foam's durability pretty quickly. So consistency is just paramount.
Which brings us to how they actually make this stuff on a huge scale. You mentioned slab stock production.
Right. That's the dominant method for mattress foam. And it's designed specifically to manage that precision and heat control.
Okay, slab stock. Paint us a picture. What does that actually look like?
Imagine a very long conveyor belt, maybe moving inside a tunnel or enclosure, precisely measured streams of the liquid chemicals, polyol, isocyanate, water, additives are poured onto the start of this belt.
Okay.
They immediately start reacting and expanding upwards as the belt moves along. So you get this continuously forming massive block of foam rising up like a giant, endless loaf of bread.
Wow. Okay. And the tunnel part, that's for control.
Exactly. That enclosed environment lets manufacturers precisely control the temperature and humidity, managing that exothermic heat release. It ensures the cell structure is even all the way through the block, meter after meter. That's the key to efficiency and avoiding those defects.
So you end up with these huge, long blocks of foam. But they're not ready to use straight away. There's a waiting period.
Correct. They need to cure. Depending on the exact chemistry, these blocks need maybe up to 72 hours to cool down fully and for all the chemical reactions to finish and stabilize.
72 hours. 3 days.
Sometimes, yeah. It's a crucial step. You can't really cut or work with it properly before it's fully cured and stable. And during that time, they often use automated systems to monitor the internal temperature and check for consistency. Quality control starts early to catch any issues before you spend money cutting it up.
Right. So after 3 days, give or take, you have a perfect, massive block of foam. Then comes the part where it actually starts to look like a mattress.
That's right. The block goes into fabrication. It gets sliced into sheets of various thicknesses or cut into more complex shapes, profiles with different firmness levels.
And this is where the layering comes in. You almost never see a mattress that's just one solid chunk of foam. Why is that?
Well, different parts of your body need different things. It's all about function. You want softer, maybe lower density foam near the top surface.
For comfort, right, pressure relief.
Exactly, for that initial plushness. And to cushion areas like your shoulders and hips where you have more pressure points.
Makes sense.
But underneath that, deeper down, you need firmer, higher density layers. These provide the real structural support, keeping your spine aligned properly so you don't wake up sore.
So that's what they mean by zone support sometimes, different firmness in different areas.
Often, yes. Or simply layering firmer support cores under softer comfort layers. It's about engineering the right blend of comfort and support. That's what creates a high-performance sleep surface.
And it's not just stacking flat layers. The sources talked about advanced cutting, making channels and contours.
Yes, that's another layer of sophistication. They use high-precision cutting machines, often computer-controlled CAD systems.
Like CNC machines.
Essentially, yes, to cut intricate shapes, channels, or patterns into the foam layers.
Is that just for looks?
Not at all. It's pure performance engineering. Foam is a good insulator, right? It can trap heat.
Oh, right. Sleeping hot is the worst.
Exactly. So those channels and contours are designed primarily to improve airflow through the mattress layers. They help dissipate body heat and moisture, regulating the temperature under you, keeping you cooler and more comfortable.
Ah, okay, that makes a lot of sense. Now let's shift to something really important for anyone buying a mattress. Safety. What's actually in the foam? The CertiPure label came up. That sounds like a key thing to look for.
It really is, especially with foams. People understandably worry about chemicals or emissions. CertiPure acts as a kind of reassurance. It's a voluntary standard, widely used, especially by European producers.
So what does it actually tell you, the consumer? What's the guarantee?
Well, it guarantees a few important things. First, that the foam is made without certain substances that have raised concerns historically, things like heavy metals, mercury, lead, certain flame retardants, and specific orthophthalate plasticizers.
Okay, none of the bad stuff.
Right. And maybe even more importantly for everyday use, volatile organic compounds.
Off-gassing.
Exactly, off-gassing. CertiPR ensures the foam contributes minimally to indoor air pollution, which is crucial for a product you spend hours close to. It confirms the foam is stable and safe after that curing process we talked about.
That level of transparency is definitely helpful. Okay, looking ahead now, the industry knows it can't rely forever on fossil fuels. What's happening on the sustainability front? Are they making real progress?
They are, actually. It's becoming a major driver of innovation. For example, using recycled polyols is becoming more common.
Recycled polyols, where do they get those from?
From old foam products, used mattresses, furniture cushions, even carpet underlay, they chemically process that waste foam to recover the polyol component.
And that can go back into making new foam.
Yes, partially replacing the virgin oil-derived polyols. They're also increasingly incorporating renewable raw materials like polyols derived from plant oils, which reduces the carbon footprint.
And they track this.
Oh, yes. They use tools like life cycle assessment, LCA, the sources mentioned Pure LCA, to measure the environmental impact across the whole production chain and find ways to improve.
That's encouraging. But what about the really long-term picture?
Yeah.
Making foam truly circular.
That's where chemical recycling comes in. This is kind of the next frontier and potentially a game changer. It's different from just shredding old foam for padding.
How so? What makes chemical recycling the big goal?
Chemical recycling uses processes, sometimes involving solvents or heat, to actually break the complex polyurethane polymer chains back down into their original building blocks, particularly the polyol.
So you get the raw ingredient back.
Pretty much. You recover polyols that are chemically very similar or sometimes identical to the virgin ones. These recovered polyols can then be used to make brand new, high-quality foam, closing the loop.
Wow. So you can make a new mattress partly from an old one. What's stopping this from being everywhere right now?
Scale and complexity, mainly. You need efficient collection and sorting systems for old mattresses to get clean foam feedstock. And the chemical processes themselves can be energy intensive and need further development to be truly cost effective and energy efficient on a massive scale. But the potential is huge. It means the valuable materials in your mattress today don't have to end up as waste. They can become the raw materials for tomorrow's comfort.
Okay, so wrapping this up, we started with this seemingly simple foam. But it turns out its creation involves really precise chemistry, large-scale industrial processes like slab stock, and now a serious push towards high-tech sustainability and recycling.
Absolutely. The takeaway is that modern mattress foam is a highly engineered material. And if this innovation in chemical recycling keeps accelerating, maybe becomes more efficient, we could genuinely get close to a circular system. Imagine a future where the main ingredients for your next durable, comfortable mattress actually come from your last mattress, which leads to the final thought for you listening. How fast can this circular foam economy really take off, and realistically, what percentage of your next mattress might actually be built from recycled old ones?
So it's definitely something to ponder. Hopefully, you now feel you have a much clearer picture of the science and the future shaping the comfort beneath you every night.